instances in litigation where someone's trying to sue someone else and they say, my system's failing, I'm going to sue the contractor, they put in faulty materials, and that's why I'm having an issue. We do a test, it's called a metallographic test, which means we actually look down at the molecular level, at the granular level of the steel. We look for any defects. We look for any abnormal steel structure. We look for anything we can find. Out of the 5 to 10 of those professional witness cases we operate in each year, we have never found a piece of pipe that does not meet the ASTM standards. Now, there are some things about the ASTM standards that kind of cause us some issues. We'll go into those. In fact, one of them's coming up. But as far as the pipe not being made to specification, we've never come across that. It doesn't matter if the pipe comes from Pittsburgh or Korea. Same difference. You would disagree?
Yes, sir. I can prove it.
Okay, I'd be happy to talk to you about it at lunchtime. But as far as we've done, and we've done thousands of pipe samples, we've never found it. But I'd be more than happy to discuss it. Number 4 is galvanized pipe. So if anyone here has a dry system or a pre-action system, I'd be willing to bet it's galvanized pipe. The industry started using galvanized pipe because they thought it was a good response to the corrosion issues that these systems face. Because when someone says, I have a dry fire sprinkler system, the immediate uneducated person that doesn't deal in our industry would say, well, it's got to be dry on the inside. That's what they call a dry fire sprinkler system. The fact is the inside of these systems are not dry. They're extremely moist. Some of them hold tens of gallons of water in them. And where that water pools, you have issues. The galvanized pipe was thought to be a good solution because when you galvanize a piece of metal, what that means is you take a base metal, substrate metal, like steel, you put a layer of zinc over it, that zinc will then oxidize and it forms that, what we call the galvanization layer, that dull gray looking color that's a zinc oxide. And what it does is it prevents oxygen from getting down to the steel. So what the industry found out, well, actually the auto industry did a bunch of research on this in the 80s. And what they found out was in a persistently moist environment, that zinc layer will actually refer to as zinc hydroxide, and it will actually come off the base metal. So then you get little areas in the base metal that are exposed and that they will corrode preferentially. That's why in a galvanized system, if you ever look at a leak, you're going to see a very defined, very aggressive pinhole, and maybe the area around it is not experiencing anywhere near that amount of metal loss. We'll talk about that a little more later, but that's just kind of an overview of the galvanized steel problem. People say, well, why don't we galvanize steels outside? You know, we use it in signposts and guardrails and all that good stuff. Why does it work so well out there? And it's simply because after it gets wet, it's allowed to dry out. If you were to take a galvanized piece of pipe and take a 5-gallon bucket, fill it with water about halfway and stick it in there, at about 60 days, you would see all this white fluffy stuff coming off the pipe at the water level, and that's the zinc actually coming off the pipe. At about 90 days, you'd start to see an orangish color. And anytime you look inside a galvanized system, anytime you look inside a galvanized pipe, you see orange or black or pink or any color other than white or gray, you've already breached your zinc layer because what you're seeing is an iron oxide. So you're already experiencing significant levels of corrosion. Number 5 kind of goes back to, it relates to number 3. And if you look at that picture, a lot of people looking at that would say, well, that weld wasn't done right, and that's why the pipe failed. It wasn't welded properly. There's actually a phenomenon called heat-affected sewn, and what it refers to is when you take a piece of pipe, because we don't use seamless pipe, and we actually take a flat piece of metal and we roll it and we weld it together to form our pipe. It's a much less expensive way of producing pipe, and that's why we use it. But what happens when you roll those two edges of metal together and you press them together and you apply heat in the weld metal, what you end up doing is on either side of that weld, you significantly heat the other metal, the surrounding metal. What that does is it changes the granular structure of the metal. It makes that metal look different on a granular level than the surrounding metal. And corrosion does one thing. It looks for differences. Whether it looks for differences in types of metals, and that's where you get into galvanic corrosion, which is you have two dissimilar metals you put together, they'll corrode, or whether it's looking for differences in the granular level of the steel. It's going to look for something that's different, and that's where it's going to preferentially attack. if we took one of these tables and imagined it as a sheet of steel, and I took a ball peen hammer and I hit the middle of that sheet of steel and we put a little bit of water on it and let it sit, the first place that would oxidize would be where we could form the steel with that ball peen hammer.
I have a question.
Yes, sir.
In a horizontal application, should the pipe seam be facing upward, or does it matter?
That's a great question.
Can you repeat it, because they probably won't be able to hear?
So the question was, in a horizontal application, should the pipe seam be oriented to the top of the pipe where it wouldn't be as likely to be exposed or underwater? And that's absolutely a great idea. What we find though is in application in the field, it's hard to do. And I'll give you a perfect example. In a like a warehouse system or system where you have pendant sprinklers, the fab shops a lot of times use that weld seam to line up the weldolets for the sprinklers that they're going to put in. So it's inherently going to be on the bottom of the pipe. In practice, if you could put it at the top of the pipe, absolutely. It would absolutely be on. But it's one of those things that's hard to do. But good question. And then number 6, it really deals more towards behaviors than the actual materials in the system. And that's, we've conditioned ourselves as an industry to think that we have to replace systems that leak a lot. What we're going to get into here in a second is corrosion's highly localized because we talked about we need oxygen, we need water, and we need the steel. Well, the oxygen has to dissolve into the water to react with the steel. And oxygen doesn't like moving through water. It doesn't move very readily through water. So what you're going to find is the majority of your corrosion is always going to be localized to where that air-water interface is. Okay, that's why if you have an attic system that's wet, or we probably don't have those out here. If you have like a warehouse that peaks in the middle, and you actually went and looked and said, you know, if we looked at where all your leaks were, most of your leaks, 99% of your leaks are going to be on either side of that peak, where you have trapped air in the middle of it, and then you have water on either side of it, and where that air-water interface is where the aggressive corrosion is going to happen. And the reason it happens so fast there is because the kinetics of corrosion are very quick. Oxygen corrosion moves very quickly. So if you take your car through the car wash and you stop to vacuum it, if you look at your brake rotors after you vacuum your car, they're going to be rusted. It's like if you go out after work or at lunchtime and it's rain, you're going to have flash rust on your brake rotors. And that's simply because oxygen corrosion is the most aggressive form of corrosion. It's just, it'll remove metal quicker than hydrogen sulfide, carbon dioxide, or any other gas. So let's talk a little bit more about weld seam corrosion. This is just a visual on it. What we're going to do, when you weld two pieces of metal together, you have to be cognizant of 2 things. The heat affected zone is one of them, but you also have to make sure that the weld metal you're using is compatible. So obviously the weld metal that we use when we fab pipe is compatible. The thing we have to worry about is the heat affected zone, which is illustrated here. It's either side of that weld, it gets hot, it actually changes the structure of the metal. And so these areas are going to corrode preferentially. The only way to fix that is to do heat treating of the pipe. When you heat treat the pipe, you put it back through the furnace, you heat it all up to a uniform temperature, about 2,000 degrees, and then you let it cool uniformly. That makes all the granular structure of the metal look the same again. We can buy heat treated metal. It's more expensive, and so we usually don't do it. But even if we did change our standards to require heat treated metal, such in the oil and gas industry, that's the only type they use is heat treated for this exact reason. We would still have issues because of the way we fabricate our pipe. We weld manifolds together. We weld weldolets for sprinklers onto branch line. So if we wanted to take care of this heat affected zone, we'd actually have to fab the system up, put it through the heat treater again, and then install it. So it's not very practical. So what we do when we look for solutions here is we try to find things that will fit within our industry that are practical and cost effective for what we're doing. So that's just illustrating after you heat treat it, everything looks the same as far as corrosion is concerned. There's a picture of weld seam corrosion. You can see the deepest metal loss is actually along the weld seam, but then on either side of it, you have fairly significant metal loss as well. So this would be illustrative of if you had that weld seam on the bottom of the pipe and there was water sitting over it, this is what you'd expect to see. This is the type of corrosion when we say we see leaks within 12 months of installing a system, it's usually almost always because it's on the weld seam. It just accelerates the corrosion that much more. So now that we talked about that a little bit, let's talk about what influences corrosion. So what will affect corrosion, what will speed it up. And when we go through these things, I think most of you are gonna think back to probably something specific to one of your systems or something you've seen before, and you'll say, yeah, that makes sense. So when we talk about corrosion, and we've already identified that it's oxygen corrosion, that's our issue. So logically, we would say more oxygen's gonna create more corrosion for us. So when we talk about a sprinkler system, we talk about pipe, we talk about water, and a lot of people tend to think of, for instance, a domestic water supply, or like a point A to point B transmission pipeline. But really all a fire sprinkler system is a big tank. It's just a big vessel. Because what we do is we take an empty pipe network, we fill it up, and then we just let it sit there. We don't flow water through it on any type of regular basis. So when you think of it that way, every time you drain the system down, that piping network is going to be filled with atmosphere. Atmosphere is 21% oxygen. Then every time you go fill that system back up, that oxygen, that trapped air, doesn't have anywhere to go. So we end up compressing it to the top, to the high points in the system, and it sits there. And until it reacts, it'll continue to sit there. So what we found is if you just let a fire sprinkler system, you fill it up and let it sit, after about 90 to 120 days, all that oxygen will have reacted. You will have taken all the oxygen that was in the gas, it will have combined, it will have dissolved into the water, it will have oxidized the metal, and now it's sitting in your system as iron oxide. And iron oxide is significantly less dense than steel is. So that's why you just see volumes and volumes of rust come out of these systems, or when you open up pipes, it might be half full of iron oxide. It's because when that oxygen bonds with that iron, it's actually less dense product. So we know the more we drain and fill, the worse it is. So the more TIs you do, the more head relocates or anything like that, the more problems you're gonna have. Dry pipe fail faster than wet pipe. So having talked about bullet point 1 right there, can we all just kind of think of why that might be? In a dry system, what do we have? We have a compressor because we have to keep our supervisory air pressure on the system. Well, the compressor is essentially an infinite source of air. The reason we have to have a compressor is all dry systems will leak given enough time. So the leakier your system is, the more air is going into it, the faster it's going to corrode. It kind of forms this little death spiral. So the more corrosion you have, the more leaks you have, the more you're going to have. And so that's why a lot of people get to the point where they think they just have to replace the entire system. So if you have a dry system that's burning up compressors, that's a pretty good indicator that you've got a pretty leaky system. If you're not already seeing a lot of leaks, you're going to be seeing them pretty soon. Galvanized systems fail faster than black, and we talked about that just now. So the reason is just because the galvanized metal is not an appropriate source of metal for pipe. When we keep it wet, which we can't dry it out, because even if we say we're going to pitch the system twice as much, or even as much as 10 times as much. Now I've worked on projects where they've taken the required pitch on a dry system and multiplied it times 10 because they happen to have the room to do so. The problem is, whenever we hydrostatically test these systems, which we have to do on every initial acceptance of the system, we're going to leave enough water in there to support corrosion. And another ironic thing is, the thinner the pool of water, the faster the oxygen can dissolve into it and react with the steel. That's why the brake rotor example is such a great example, because it just gets water wet and it happens so quickly. So any dry system isn't really dry, and when we compound that by using a galvanized piece of metal, we're going to have failures a lot faster. And when I say a lot faster, I mean 3 to 4 times faster than what you're going to see in a black steel system. Same schedule, so Schedule 10 black to Schedule 10 galvanized. And we've seen failures in as little as 6 months out in Reno, Nevada. And that'll make sense here in a second when we talk about why that was. It actually had to do with the outside temperature. Level of activity, that goes back to the more oxygen you put in, the more corrosion you're gonna have. Because every time you drain and fill, you put more oxygen in. System design, trapped air water. So if you go look at systems, some systems are designed such that even wet system, or even dry systems, such that they're not drained as the code would require them to be drained. They don't have auxiliary drains where they need to be, and they're trapping a lot of water. In wet systems, the same thing can be said for air trapping. So the way we design systems like, for instance, if you had a mezzanine level or something like that, where you had a system and then you came up and we're catching a mezzanine level, all your air is going to be pushed from the entire system up to one locale, in a sense, in that mezzanine piping. So we're going to take all that oxygen from the entire system, instead of distributing it out over all the high points of the system, we're going to stick it in one spot, and that'll cause you problems as well. Quality of system installation. And what I mean by this is we're going to go back and talk about pitching. Pitching is a big deal in dry and pre-action systems, and it's in there for a reason. It's in there to get the water out, okay? So we're trying to keep as much water out of the system as we can. But the problem is, even if you have the best fire sprinkler contractor install your system, and they put it in, and everything's pitched perfectly, what happens is other trades are going to come in over the life cycle of the building. There's going to be, a new HVAC duct run or a new electrical duct bank run, and someone's going to come in. They're just going to say, "Well, I need to get through here, so let me just lower this hanger." The building settles. The system settles with the building. So you're almost always going to find those spots in the pipe that collect water. So that's always an issue, and that's something you can have your contractor look at for you if you're having a lot of problems. Is my system still pitched as it's supposed to be? And this is the really interesting one. Higher temperatures increase corrosion. So corrosion is just a chemical reaction, and any chemical reaction is influenced by temperature. The higher the temperature, the faster the reaction. So a general rule of thumb in chemistry is 18 degrees Fahrenheit. An increase of temperature of 18 degrees Fahrenheit is going to double your reaction rate. If you go 18 degrees, you're double. If you go 36 degrees, you're quadruple. If you go another 18 degrees, you're going to be 8 times the corrosion rate you were at room temperature. It works the same way. You decrease the temperature by 18 degrees, you half the rate, quarter it, an eighth of the corrosion rate. That's why in cold storage areas, not freezer areas, but cold storage areas, you don't see a lot of corrosion. The temperature is so low that it retards the corrosion rate so much that it just doesn't really become a problem. In freezer applications, you don't see any corrosion because you don't have liquid water, you have ice. But if you think about the higher temperatures, your attic systems, your large warehouses that aren't conditioned, those all suffer greatly from corrosion. And that was the dry system I was talking about. It was an outside home and garden center, and they had a galvanized Schedule 10 dry system that was installed. They had their first leak in 6 months in Reno, Nevada. So it's absolutely an influencer. I can tell you that one of the first places that we really made this correlation, we went into, once again, a big box home retail goods store. They had 3 identical systems. They were basically carbon copies of each other. And they said, system 3 is causing us a lot of issues. We think it's infected with MIG. It's having a lot of leaks. System 1 and 2, we have no problems. So they said, would you please come out here, confirm it. We want to get ahead of it before it infects systems 1 and 2. And we said, well, we don't think you have a MIG problem. It's oxygen corrosion, but we will be happy to come out and see what's going on for you. So what we did, we devised a plan. We were going to take pipe samples from each zone. We're going to take all kinds of measurements, and we're going to go back to the lab and look at the pipe and see what we can figure out. Well, we took our pipe samples from system 1. We took our pipe samples from system 2. We got to system 3. It was noticeably hotter in system 3 at the roof deck than it was in 1 and 2. So we took our samples. We came down and we asked them. We said, we got to looking, and we said, well, what's going on here? And what happened was that was where the lumber yard door was. That's where they drove the fork trucks through to load the lumber trucks. And we said, well, how often is this door open? They said, well, during business hours, it's open almost all the time. So we went and got a thermometer, and we measured the temperature as 60 degrees warmer in that bay than it was in the other 2 bays. And so that's what was causing that one to experience so much more corrosion. So if you think back to that, I've been in big process warehouses where they use hydraulic presses, like 300-ton presses, and above those presses, those pressing lines, the temperature was 50 degrees warmer than it was in their paint areas and their raw material storage and their finished goods storage. And if you plotted out all the leaks they had experienced and fixed over time, they were all concentrated over that area where they were doing the press work. So when we start looking for why corrosion's happening, where it's happening, these are the things we're gonna look at. These are the questions, if you called me, I would ask you a form of all of these questions. And we tried to figure out what was going on with your system, or if we walk the system, these are the things that we would look for. And once you start thinking about it, once you start looking at it in the real world application, you're gonna find that once you know these things, you can walk into almost any building and say, you know, I can tell you where your problems are just looking at this. So every instance, and I'm gonna hit on this more than once in this presentation, every time we repair a leak, corrosion is cumulative and we're gonna create another leak. So we keep taking metal off the pipe wall. So one of the things we did, we got kind of curious, and in all the systems that we touched, we wanted to know what is the average service life, if there is such a thing for a fire sprinkler system. So we started looking at all the data we collected throughout the years, and we said if we take everything out and we only separate the data by if it was a black system or if it was a black pipe wet system or a dry pipe galvanized system, what is the average lifespan? So we said, we're not gonna pay attention to what schedule the pipe is, we just wanna know wet or dry, what's the average lifespan? 15 to 25 years for wet systems is what we found. And what we found, 10, 12, 15 years is when we start getting significant leak issues. Dry systems were 10 to 15 years. You start seeing leaks in the 3 to 5 year range. If someone calls me and tells me they have a galvanized dryer pre-action system that's Schedule 10 and it's 5 years old and they haven't had a leak yet, you know, I tell them you're doing well, because usually by 5 years you're going to have a leak. So like I said, that is just a very generalization. I'm sure you can all tell me right now, raise your hand and say, well, my system's 40 years old. But like I said, we just kind of looked at a global overview of everything that we've touched over the years. So when we talk about, yes, right.
Adam, I had a question from the gallery. It says, is there benefits to ventilating the attics to reduce the temperatures?
So the question is there benefit to ventilating the attic to reduce the temperature? Absolutely. Anytime we can reduce the temperature, we're going to reduce the corrosion rate. So that absolutely would help, for sure. I don't know how much you could reduce the temperature, but any reduction in temperature would improve the corrosion resistance of the system. So the other thing we did is we started to realize, yeah, we're a company that makes things and we do consulting work, but we're really a risk consultant. People really come to us to help them lower their risk exposure. And when we start looking at a risk spectrum, and how you assess risk, we look at two things. We look at what type of facility you're operating or what type of processes you're doing in that facility, because that tells us what type of risk tolerance you're gonna have. So if you look over here on the left, a parking structure, you know, we have a leak, a car gets wet, it's not the end of the world. At the other end of the spectrum, you have your data centers, your mission critical environments. You have a leak, the East Coast FAA radar system goes down for 45 minutes. And that actually happened. They estimated the loss of $100 million. So different people care differently about corrosion control. And that's absolutely relative to how much risk tolerance they have for their business process, how much risk can they take on. The second thing we did is we said, all right, now we understand the types of buildings we have or the business operations we have, and we know what kind of risk they can tolerate. Well, let's look at the types of sprinkler systems and the risk they represent from a corrosion standpoint. So on the moderate risk side of the spectrum, we have the wet systems, the Schedule 40 systems at Black Steel Pipe. They last the longest of any fire sprinkler system. On the other end of the spectrum, we have the dry and pre-action Schedule 10 galvanized. Now, what I point out and what's I think is kind of funny is we take our lowest risk tolerance and we put our highest propensity to corrode and create a leak, our system over that. Now there's other reasons we do this, and we do it because we don't want water sitting over the systems. But the funny thing about that is, remember when we talked about you have to have liquid water to have corrosion? So in a dryer pre-action system where you get your pinhole leak, we'll have some amount of water sitting there. So at least initially, you're gonna get some water come out of that hole as soon as it reaches the outside of the pipe wall. So that's what we do. I mean, we really approach this from a complete engineering perspective, and we're really looking at business continuity, we're looking at life safety, and we're looking at how the systems operate. And that leads you to, there's really two distinct groups, and they care about different things. There's a group that cares about life safety and structure risk. And not that the other group doesn't care about that, it's just not necessarily at the very top of their list. These people are your fire marshals. You know, they've dedicated their life to protecting people and property, and they're charged with enforcing the building codes, the NFPA standards and things like that. So when they look at a system and they look at it from a corrosion standpoint, they're concerned of, is this system gonna hydraulically operate as it was designed? Is it gonna control the fire as it was intended to? Is it gonna protect life and property as it was meant to? The other group of people are gonna look at it from a little bit different perspective. They're gonna look at how much does it cost me to maintain a system that's experiencing corrosion? What structure and property risks do I have? But most importantly to business operators is business continuity. How is it going to impact my ability to generate revenue, which is why they're in business? So those are our property owner concerns. Like I said, people, you know, they cross over between these groups, but what's really important to them varies a little bit. And corrosion affects all of these things. Corrosion will absolutely affect the ability of the system to control a fire or suppress a fire as it's designed. FM released a study about a year ago, and it said in 68% of the instances where the fire sprinkler system failed to operate as designed, it was tied back to because water didn't get to the area it needed to get to. Now, it doesn't say necessarily that's because of corrosion. It could be someone closed a valve. It could be, you know, it wasn't necessarily designed appropriately hydraulically, but corrosion is definitely in there. And we'll look at some pictures and I'll show you why corrosion affects how the system operates. This is what we were talking about earlier, the leak frequency curve. Once again, this is to illustrate corrosion is cumulative. Once the metal comes off the pipe, we can't ever put it back on. There's nothing we can do. We can only stop the corrosion at some certain point and preserve what pipe wall's left. So as we look at this and as we think about every time we repair a leak, we're gonna have enough oxygen go in to create another leak, our leak frequency goes up. Our expenditures to maintain that system go up. Well, at some point, I've been involved in projects where the fitter can't even get off site before they have another leak. So these systems can get very bad. I mean, we can talk 5 leaks in a week, almost a leak every day, you know, if it's allowed to get that bad. But usually at some point, the owner, building owner, operator, whoever's responsible for operating the property is going to come in and say, look, we can't do this any longer, whether it's the cost of maintaining this system as it is, or whether it's the business continuity disruptions that it's causing, we need to rip the whole thing out and put a whole other one in. So the question, and I think I even heard this before we got started, people will tell me, and they'll talk amongst themselves and say, you know, I've got a system that was put in 1940 and I've never had an issue with it. And yes, those systems are out there. But when we say, well, why did that system perform so much better than the systems we're installing now? For instance, the systems we installed in the early 2000s that are already having leaks. Excuse me. Well, as an industry, over time, we've changed the way we design the systems. We changed the way that the materials that we use to install the systems, and our standards have changed as to how we test the systems. So the first thing is thin wall branch lines. You know, in the 80s, we started using thin wall pipe. And we did it for a couple reasons. One, you get better hydraulics because you have a larger inside diameter of the pipe. So it can save you going up in pipe size, or it can save you a fire pond. The other thing is less material. So your material costs are lower. So we started using thin wall branch lines a lot, especially during construction boom when everyone's just trying to get things up as, yes, right?
Thin wall schedule 10, so some people understand that.
Right, schedule 10 or even thinner, yes, yes. So Dynaflow, if anyone has so anyone has Dynaflow XL pipe, those are all threadable thin wall, sometimes it's called. Those are all even thinner than Schedule 10. So just to give you an idea, and a 2-inch line size, Schedule 40 is about 120 thousandths of an inch, Schedule 10 is about 90 thousandths of an inch, and these threadable thin walls can get down into the 60s and 70s. So if you're talking threadable thin wall or Dynaflow or Excel, and you look at it compared to Schedule 40, you have about half the pipe wall thickness. So it just has less metal to get through, it can get through it faster. Galvanized pipe on dry reaction systems. FM started requiring you to put galvanized pipe in. So if you're underwritten by FM or your insurance carrier is FM, they're going to tell you, their 2.0 data sheet's going to tell you, you have a dry pre-action system, you have to use galvanized pipe, no ifs, ands, or buts. They've actually changed that data sheet now. It does say you can use black steel pipe if you use nitrogen as your supervisory gas source. So they are moving a little bit in that direction. Just like any other standard, any other governing body or organization, it takes time to move these things, but they are recognizing the benefits of using black steel and when you use nitrogen. So and we have a lot more dry pre-action systems than we used to have. I mean, think of all the computer rooms, the data rooms, the server rooms, telco rooms. We just have a lot more dry pre-action systems, so it's coming to the front of mind a lot more. Gridded design with elevated branch lines. So at this point, I'm not saying do not use gridded systems. Gridded systems are wonderful, they're great. What I want to point out to you is when we change the way we design systems. So the old way of designing a system is what was called a tree system, a pipe schedule system, and what it was is you had a main run, you had branch lines come off that main run. When we were able to start using computers, such as this one up here, we could hydraulically calculate the system. So we no longer had to depend on hand hydraulic calculations. It allowed us to get much more complex in our system design because we could calculate them on an individual basis. Gridded designs are very good because they give the water multiple paths to get to a sprinkler. They're very hydraulically efficient. The one thing is, there's a lot more pipe volume in a gridded system than there is in a tree system when it's covering the same floor space. So what that means is there's more oxygen inside the pipe that gets pushed to an area. There's more oxygen molecules available to react with the pipe wall and remove pipe level. So once again, I'm not saying don't use gridded systems. I'm just trying to explain the evolution of fire protection design and how it adversely affected the corrosion. Lack of heat annealing, we talked about that. As an industry, we can't really practically heat anneal on our pipe. It would be cost prohibitive. Just like we can't go to seamless pipe, it would be cost prohibitive. It just, in our industry, it's not a solution, so we just need to find a different way. Trapped water in all dry pipe systems. If you watch a fitter and he goes and opens a dry system, I guarantee you he will always at least have a 5-gallon bucket with him. And if he doesn't have a 5-gallon bucket, he probably has a 35 to 50-gallon trash can on the wheels with him. There's water in the dry systems. In remodel activity, this is very apparent mall operators. So your local mall, they suffer from corrosion more than almost any other type of building use group. And that's because they have an overhead system that might protect 5 to 7 inline tenants. Well, anytime any one of those inline tenants makes a change, that system gets drained. So it's getting drained and filled, 2, 3, 4 times more than your average system would be in a retail or office occupancy, maybe even more than that. Once again, corrosion is cumulative. We'll put more oxygen in, we're going to have more corrosion issues. And then from a testing standpoint, from a governing standard standpoint, we're required to take our systems up and down a lot more. We're doing our 3-year trip tests on dry pre-action systems. We're doing our 5-year internal obstruction investigations. We're doing a lot more with that. And another point that's not up here that is a good point is our inspection tests and drains, our remote test stations are at the riser more now. They used to have to be out remote on the system, like your hydraulically remote location. And what that actually was doing was providing a vent. It was actually, what would happen was when they fill the system, a lot of times they'd leave that remote test station open and it would let all that air get out. So that was another thing that changed with the code that affected us, because now when we fill these systems up, a lot of times there's nowhere for the air to go, it just stays in there.
Which the air staying in there that's a good thing, right? You put new air in, you're talking about more corrosion.
Right, so when you drain a system, a lot of times what will happen is your fitter will open your main drain, and then he'll go open an auxiliary drain if there is one, or some remote part of the system, because what that does is it relieves the vacuum that's created as the water's leaving the system, and it lets the system drain faster. But the side effect of that is it's sucking new atmosphere out. So almost every time when you drain a system, you're going to have that fresh oxygen in the pipe. So you definitely want to get that out if you can. So this is when we talk about, okay, here's how corrosion happens, here's why it's happening, here's the influencers. Well, the next logical step is, well, what do we do about it? And there's several things we can do about it. You know, if you have a system you think is to the point that it needs to be replaced, we can come in and look at it, we can assess it, we can actually do pipe samples, or we could do a video scope assessment. We could get down to that percentage of pipe that needs to be replaced, and we could keep the rest of your pipe. So instead of doing a complete system replacement, we do what we call surgical pipe replacement. So then we can deploy a corrosion control system, because if we don't do anything to address the corrosion, unfortunately, you're going to be in the same shoes in about 10 years down the road. And then the important step is monitoring the corrosion. We need to know that whatever we're doing to control the corrosion is actually working, the system's being maintained properly, being applied properly, and that everything's working as it should be. So this is just real quick. If you were going to assess a system, there is a right way, and there's an effective way, and then there's an ineffective way. The best way to do it is we want to review the system, we want to see plans on the system, we want to understand the leak history of the system, but the most important part is the video assessment. That's where we get into the pipe and we actually look real time at the pipe, the conditions that are going on. There's another type of pipe sampling, pipe assessment out there. It's ultrasonic testing. They call it non-destructive testing because they can actually test from the outside of the pipe without taking the system down. FM has just released a paper on it. It said because of the localized nature of corrosion in fire sprinkler systems, they do not endorse ultrasonic testing. We used to do ultrasonic testing, but because of the lack of reliability of the results we were seeing when compared to video assessment, we completely stopped doing it. I would encourage you, if you're going to make the investment to do any type of assessment work, to look at a video scope. They call them borescopes. It's essentially a camera on the reel, and to kind of stay away from the ultrasonic testing. And then this goes back to, well, when we do an assessment, what do we find? We find generally 80% of the pipe is fine. We don't have to replace it, and we can go in and just replace 20% of the pipe, save a lot of money, save a lot of downtime in an operating facility, and get you back up and running with a system that has been remediated from a corrosion standpoint, and go from there. Because corrosion is highly localized, and I told you I was going to say that multiple times. Because we're looking at that air-water interface, those are the areas where we're going to be experiencing the corrosion. If we can replace the pipe in those areas, we don't have to go back and replace in a wet system. We don't have to replace all the mains. We can concentrate on branch lines. In a drier pre-action system, we don't have to replace all the branch lines most of the time. We can just replace sections of main, because that's where we're getting that air-water interface. Wet, trapped air, so high points. Dry, trapped water, so low points. What I want to get at here is when we've identified oxygen as the corrosive agent in the fire sprinkler system, it's important to understand where that oxygen is coming from. When you look at a system that's been pressurized at 75 PSI, about 16% of that system is trapped air by volume. The rest of it is just fluid-packed pipe. The pie chart on the right is then looking at the oxygen available to react in that system. And the big red section, which is 99%, that's the oxygen that's contained in the trapped air. That little sliver that's 1%, it's actually a little less than 1%, but the pie slice becomes so small you can't see it. That's what's coming in with the water and the dissolved oxygen content. To address the dissolved oxygen in the incoming source water is not you don't get a return on your investment. It's not making a significant difference in corrosion control. What you want to do is you want to address the trapped air in the system, whether that be in the dry system, your supervisory air, or whether that be in a wet system, the air that's contained in the pipe network before you fill it with water. So if someone's coming to you and they're telling you that you need to treat your incoming source water for dissolved oxygen, you don't need to do that. Where that comes from is in like steam generation. If you're generating steam, you absolutely need to control the dissolved oxygen in your incoming water source. But that's because you're operating at much higher temperatures and much higher pressures. Once again, we have to look at not just corrosion in general, we have to look at the guidelines, the technical specifications we operate in as an industry. The temperatures and pressures we operate at, 8 parts per million, 10 parts per million dissolved oxygen in the incoming water source, which is what you'll usually see from a domestic water supply, is not an issue at all. This is just a visualization of what's happening. So if you imagine a cross-section of pipe, you're looking at your trapped air up here, you're looking at your water. Where the water dissolves, the oxygen dissolves into the water, we're gonna get our corrosion. That's why you see at the air-water interface, when we look at some pictures of pipe, you see a lot of corrosion right there at the air-water interface. You're also gonna see some corrosion byproduct there at the bottom of the pipe. That's just because the iron oxide is it's not tenacious, meaning it doesn't want to stick to itself, so it wants to come off the pipe very quickly. So it tends to accumulate at the bottom of the pipe. The other thing is when you move water, fill the system, drain a system, this stuff moves very readily throughout the system, so it'll accumulate at different points in the system. So this actually just was finalized at the end of, what was it, in June at the NFPA 13 convention. The 2016 edition of NFPA 13 will require a method of venting. Now, they're not going to tell you have to put a vent in. They just say you have to have a method of venting. It could be a ball valve at a high point, or it could be an automatic vent that you don't have to operate. But it will require a method of venting. And that's in recognition the standard is moving towards addressing corrosion. And they recognize that oxygen is the cause. We're moving away from MIG. The standard's moving away from addressing MIG. They're telling you that chemical corrosion inhibitors are no longer approved unless they're listed as compatible with everything you see, every material you would see in a fire sprinkler system. But really what we're addressing with a vent is every molecule of oxygen will react given enough time. So it's very simple. You remove 50% of the trapped air in your system, you're going to cut your corrosion rate by 50%. So that's when we start talking about putting air vents in and things like that. It definitely makes a large impact on the corrosion rate of the system. So here's some pictures, and hopefully these translate well. But you can see in this picture here the air-water interface in this piece of pipe where the water sat. This is a wet system. You can see in this piece of pipe even better where the air-water interface was. All of this that you're seeing, all of that orange stuff, brown stuff, that's all iron oxide. That's all rust is all that is. So you can see, and one of the things that's really interesting, if you guys look at this picture in the lower right-hand corner of the slide, you see it almost looks striped, striations on the side of the pipe wall there. A couple things you want to notice from this picture. One is the very top of the pipe where the water, where it was just air, there was no water, there's virtually no corrosion there. All our corrosion is happening below the water line. The second thing we want to notice is, while at one time this pipe was almost full of water, at another time it was just barely had any water sitting in it. And what had happened is, over the heat of the day, the water would evaporate. And when the system cooled off at night, when the space cooled off at night, this is an unconditioned space, that water vapor would condense at the top of the pipe. And then it would get enough to form a droplet, it would roll down the side of the pipe. Given enough of those cycles, it actually wore grooves in the side of the pipe. This is something you see all the time in attic systems or in an unconditioned warehouse space. Is every time that water rolls down, it's going to take a little bit more metal with it. It actually will form a groove in the side of your pipe. Just more pictures for some of us. We've seen a lot of this for others. It's just affirmation that your system's not the only one having issues. But I mean, you can see these pipes are a third halfway full of corrosion byproduct. So when this system was calculated, it wasn't calculated assuming that half of the pipe was going to be obstructed by corrosion byproduct. This system will not perform as designed, and I guarantee you this system won't meet the NFPA 13 requirement for design density that it was designed to. So it is a hazard, and I think as this becomes more of an issue and fire marshals start paying more attention to this, we're going to see our 5-year inspection test change, our visual inspection. They're going to require something more, or they're going to require some sort of corrosion control method, because the fact is this system is not going to do what it's supposed to do. Here's a video. This is a wet system. This was in a unconditioned manufacturing warehouse. But you can see once again, where the air was, there was virtually no corrosion. But you can see every one of these bumps, we call them tubercles, but every one of those bumps underneath them, there's a pit. There's a pit forming, there's a potential leak happening. So you can see that corrosion does absolutely, and you can see how rough that pipe wall was. That affects your hydraulics as well. So when we get pipe samples, they come into us, we evaluate them for corrosion. One of the things we look at, so we'll take the pipe, we'll cut it in half, we'll look at the corrosion buildup in the pipe, which is what these pictures are. We'll actually media blast that pipe so we can get down to the metal, so we can see the metal loss signature, and that's how, we're gonna look at those pictures here in a second. That's how we can tell you if it's MEG, if it's oxygen corrosion, acid corrosion, or whatever type of corrosion it is. But what I wanna point out here is when people look at pipes like this and they see orange, they see all this byproduct, they call it MEG. When they open up a pipe and it smells, they call that MEG. It's not MEG. What you're smelling is actually just the iron oxides. Now, if you open a pipe up and it smells like rotten eggs, that's hydrogen sulfide gas, then you might have a bacteria issue, but that's fairly rare. So what those pipes look like when we clean them up, this is what they look like. So in the upper left-hand corner, you can see how smooth and aggressive that hole is, that metal loss is relative to the rest of the pipe. That is classic oxygen. If you move over to the top right picture, you can see the through the wall failure. You can see how deep and smooth that pit is, what metal loss is when you look at the surrounding area. That's classic oxygen corrosion. If you have MEG, if you have bacteria-based corrosion, what you're going to see is a deep pit, a lot of metal loss, and then as you get out from that point of origination, it's going to have a stair-step function. It's going to kind of look like a canyon was formed. And what that is the colony adheres to the pipe wall and it starts removing metal. As the colony grows, it's had less time to work on the metal. So that's why you get that stair-step effect. So it's very easy to tell corrosion, what type of corrosion is by the metal loss. So if we look at the top left, the bottom left, and the top right picture, those pictures look fundamentally different than the bottom right picture. Can we agree on that? Does everyone see the differences? The bottom right picture, it's a little hard to translate in the slideshow, but those are very small holes. They're like pinholes. But those holes are very deep. They're about 70% of the way through that pipe wall. That's characteristic of acid corrosion. Where we find that sometimes is in a dry system when we have a compressor putting in moisture. So you compress air, you heat it up, it can hold more moisture. It goes into the system, it cools off, it releases that moisture. That moisture is then distilled water. Distilled water means it has no dissolved mineral content, it has no ability to buffer its pH. So what happens is it absorbs carbon dioxide out of the air in the system, forms carbonic acid, and it'll have a pH around 5, 5.5, which when you think back to what we were talking about earlier, the water is about 8, 8.5 pH. It's 1,000 times more acidic, and we actually can see acid corrosion in those cases. So that's what that is. And then this is just a well-seen corrosion again. So let's switch from talking about wet systems to dry systems. We have the same mechanics that are happening inside the system, but they're happening in a little different ratios. We have less water, we have more oxygen. And in this case, in a dry reaction system, we might have a galvanized pipe. So in a dry system, instead of looking for the high points where we're trapping air, we're looking for the low points where we're going to trap water. We have much more oxygen available, like we said, almost an infinite amount because we have a compressor consistently putting in more oxygen as the pressure drops in the system. That oxygen that's being added most of the time is going to be warm and moist. It's going to have some condensate in it. We might have desiccant dryers, we might have dry air packed systems or regenerative air coolers, but most of the time those systems are not necessarily maintained the way they should be, and we're still putting in some level of moisture. But all of that aside, remember that when you do your trip test, you're putting in enough moisture that's going to stay in the system to cause all the corrosion you're ever going to need to have a leak. So this is the same illustration, but as you can see, we just have a much thinner pool of water. As we discussed, the thinner the pool of water, the quicker the oxygen can dissolve and react with the pipe, and the faster, more aggressive your oxygen corrosion is going to be. So these are all pictures of dry systems, so you can see how much water is in dry systems. This pipe at one time was almost all the way full of water. You can see an air-water interface at the very top of it. You know, this pipe had significant amounts of water in it. Same with this pipe. What I want to show you here, what we're looking at, this is actually Heinz Field, where the Steelers play, Heinz Stadium. This is a 10-year-old dry system, but it's black steel. So what I want you to do is kind of just look at this, remember, so what we've done is we pushed up corrosion byproduct in front of the camera there. But remember how smooth that pipe wall looks, okay? We'll just go back. But remember how smooth this pipe wall looks? Yeah, there's a little corrosion byproduct in the bottom of the pipe here. But in a couple slides, we're gonna look at a 9-year-old pre-action galvanized system. It's gonna look completely different than this. So this is just one of the things we do, and one of the ways we figured out as much as we did, is we're what you call an empiricist organization. Yeah, we understand the science, and yeah, we work with the science, but we actually just a lot of times go out to the field and collect data. So that's every time we see something, something like this, it's confirmation that the book science is really applicable to what's happening in the field. So why do we use galvanized pipe as an industry? Well, it's because someone along the line probably asked someone in the corrosion field, hey, I have a dry system, what would be the best type of pipe to use to mitigate corrosion? That corrosion engineer, not knowing anything about fire protection systems, said, use galvanized pipe, it works great. Dry, don't worry about it. Well, when we talked about how we make galvanized metal earlier, we talked about a chemical reaction that has to happen. And what that is we put the zinc onto the iron, onto the steel. We get that, it absorbs some oxygen out of the atmosphere, forms a zinc oxide. Get that zinc oxide wet, it forms a zinc hydroxide. We let that zinc hydroxide dry out, forms a zinc carbonate, and we've got galvanized metal. The problem is, where that little arrow crossed out is, we don't stay in this state. If you take the zinc carbonate, a galvanized piece of metal, and you keep it consistently moist, it will revert back to zinc hydroxide. So anyone that's opened up their galvanized system, seen white fluffy material in there, that's the zinc that's actually coming off your pipe. That is the zinc hydroxide. So general rule of thumb, we're gonna fail 3 to 4 times faster given the same schedule of pipe if we use galvanized over black. This is the same reaction taking place, but what this is showing you is there is that zinc hydroxide being formed down here. The reason this is important is once we get through that zinc layer, we have a small area of iron exposed, of steel exposed. All of our corrosive energy is now going to focus on that one little point. Instead of in a black pipe system, it's going to focus on any of the leaded metal. In a galvanized system that's had a breach in the zinc, all of that oxygen is going to want to react with that one small area. That's why the failure happens so much quicker. It's because that corrosive energy is dense. It's not allowed to spread out and work on all of the pipe. It's only on the area where the zinc has been moved. This is what it looks like. So you can see orange in these pictures, that's our iron oxide. We take the 2 pieces of pipe at the top and we clean them up and we look at the bottom, especially the bottom right, you can see how aggressive that oxygen corrosion was on those breaches in the zinc coating. So the zinc coating, once it's breached, you can have failures in a matter of months. That top left picture, you can see there was a water line in there about a little over halfway up. So that's why you see all that white, fluffy, powdery stuff. That was the zinc coming off the side of the pipe. So one point I want to make here is you're going to hear people talk about, when we talk a little bit later, we're going to talk about how do we control corrosion in dry reaction systems. And the answer is we replace the supervisory compressed air source with supervisory nitrogen. Nitrogen is a dry gas. 98% the dew point's around -70 degrees Fahrenheit. We thought at the very beginning that we would be able to dry out a system by just running nitrogen through it. We thought we ran enough dry gas through it, it'll absorb all of that water, and it'll come out the vent, and we'll eventually dry the system out. So even if oxygen does get in there, there's no water to react, let it dissolve into and react to the pipe wall, we'll be fine. It's like a double layer of protection. That piece of pipe on the right came from DFW Airport. They put in a dry system and they said, you guys, we believe in what you're doing. We're gonna let you do anything you want with this dry system. So what we did was we put 4 vents on this dry system. We ran 98% nitrogen through it for over a year, about 18 months. After 18 months, we had spools at different parts of the system. We took them out, and this is one of those spools. This is not what we would expect a piece of pipe to look like with those pits that are about 50% wall loss after being under a nitrogen environment for 18 months. What we found out was because corrosion's cumulative, When we're putting in 98% nitrogen, we're still putting in 2% oxygen. You put in 2% oxygen for 18 months, you're worse off than if you would have just put an air compressor on it and just let the system naturally leak. Because we were inducing a leak rate with our vents, thinking we were drying the system out, we just let it vent continuously. You can't dry out a system with nitrogen. There's just too much water in it. The amount of nitrogen you would need would contain so much oxygen, even at 98% purity, that you would cause yourself corrosion issues. That's why it's important when we start talking about it, we're going to talk about not continuously venting. We're going to talk about getting to 98% nitrogen in the pipe network within 14 days or quicker. We want the oxygen out as quick as we possibly can. This is a piece of pipe, galvanized piece of pipe. You can't really see it, but between these two yellow arrows was water. There's a slight color variation. All the zincs come off of it. We've cleaned the pipe up. But what I want to point out is how localized and deep that pit was and how aggressive it was. The metal loss around there, there's virtually none, but we've got through the wall failure. I think that was about a 1/4 inch failure. The other thing to notice is this flow seam is completely intact. This piece of pipe was actually heat treated. Here's the video I was telling you about. So this is a 9-year-old pre-action system. What we're going through right now, this is a 2-year section that had to be replaced. We're going to go through a rolled groove coupling. That's going to be the 9-year-old section. So already you can tell there's a lot rougher surface on the pipe wall than that previous video we looked at. But as soon as we come through this coupling up here, it's going to get really bad. So that is much worse than that 9-year-old black system we looked at, or 10-year-old black pipe system we looked at. The top of the pipes at the bottom, we didn't have a self-leveling camera at this point, but you can see there's multiple air-water interface lines in here. So at different given times, there was different amounts of water in it, and you can tell at that first one near the bottom where it's almost all white, that water level didn't sit in there for very long, probably only 60 days or so. But once you get to that second water level where you start seeing those brown and black little bumps, that water probably sat in there for much longer than that. And those underneath each one of those is a pit forming and about to happen through the wall failure. So you can see, just given the same amount of time, 9 years versus 10 years, this pipe looks much, much worse than that black steel pipe did. So now we say, well, how do we control corrosion? We've learned all we ever want to know about it. So in any industry, you've got 5 ways you can control corrosion. Metallurgy. We could change to stainless steel fire sprinkler pipe. It's cost prohibitive. We won't do that unless we have some specific installation, like a food service industry. Sometimes food processing applications, they'll use stainless steel, but very rarely. As an industry, we're never going to switch to it. It's too expensive. Same thing with copper. We'll never switch to it as a standard. It's too expensive. Plastics. Well, our standards tell us we can only use plastics in certain applications, and that's in a very limited application. You're never going to see it in general industry. That's not an answer. Coatings. When I say by coatings, I don't mean you can buy pipe now that says it has a thick coating in it. I don't mean that. What I mean is an actual, epoxy phenolic is a type of coating. It's where we're actually lining the inside of the pipe with some sort of epoxy or plastic that will cure to keep, once again, the goal would be to keep the water, to keep the air from reaching the metal. We look at our industry, well, what does our pipe look like? Well, it's a bunch of seamed sections with a bunch of sprinklers coming out of it. Every time we took a pipe apart, pipe section out, or every time we unscrewed a sprinkler, we would compromise that coating. Anytime we compromise the coating, the same thing's going to happen to that happens with galvanized pipe. It's going to, all the corrosive energy is going to start getting under that coating, at that crack, at that seam. We're going to have delamination issues. We're going to have a whole slew of issues. We have concerns with plugging when it delaminates. So as an industry, when you look at that application, how you would have to apply it in situ and, when the pipe's hung, and then what would happen as we operate the system, we'll never go there. Chemical inhibitors, we tried very early on. The problem with chemical corrosion inhibitors, they work really great in flowing regimes where we have a transmission pipeline, because the way they're designed to be carried by whatever you're transmitting, oil, water, whatever, through the pipeline. So there's always a dosage in whatever you're transmitting through the pipeline to reapply if we ever get a breach in that chemical corrosion inhibitor on the pipe wall. Well, the problem in our systems is they're not flowing systems. They have a bunch of dead ends in them,
and we're relying on the water as we charge the system to apply the chemical corrosion inhibitor.
Well, the port in the system, the portion of the system where we get the least effective application of the chemical corrosion inhibitor is at the air-water interface, because the water just barely gets there. Well, where's the point that